One special case you might encounter is something called a two-force member. And this is when you have some object that doesn't have any applied forces on it, but instead is pinned at both ends. So both ends are subjected to a pin, and what that does is it has a force, right? There's an Fy and an Fx force, and this force, these two forces are the same and are acting on this same line of action. So a two-force member allows us to simplify something into a single force that before would have been multiple forces together. So we'll take a look at an example of where you might see a two-force member. So in this example, we're asked to determine the magnitude of the force on the pin at A. And this system that we have here is this system of two shapes together. There are actually two separate bodies here connected by a pin at point B. So we have this one member. This darker member here is this BD member. And this member is pinned on both ends. So both of these ends have pins going through them. And their line of action of their force is at a 45 and goes through the same point. So this is an example of a two-force member. And what that means we can do is we can treat the force coming off of this member, I'm just going to call it force BD for simplicity's sake, the force going through BD is the same coming out both ends. So instead of having to do a reaction at D in the X and Y direction and a reaction at B in the X and Y direction, I can simplify it to this one force. Right, so here I have FBD, and if I want to draw my free body diagram for the system, I would draw them separately. I draw them for each body. So this would be like the free body diagram for the I guess, right angle member. And then for this curved member, if we do this free body diagram, what I have is this 400 Newton force coming off of it. I have the reaction forces from the pin at A, so in the AY and AX directions. Those are my support reactions, which are the forces I'm trying to find, right? And then from that pinned connection at point B, instead of having a BX and a BY, instead of doing that, I'm going to say not doing that, right? I can just put in my force BD. I can represent it as just this force BD. Kind of like a tension force coming off of it, right? If it was a rope pulling on it. So now I have three unknowns, and I can apply my three equilibrium equations to find them. Before, I would have had four unknowns and three equations, so it wouldn't have been solvable. But now with this system set up, I can solve with my three equilibrium equations. So I'm going to go ahead and do my moment first, right now that I have my free body diagram. I'm going to take a moment, and I'm going to go ahead and do that counterclockwise positive sum of moments about point A. Right, so that should enable me to find what FBD is. Because I have 400 newtons, I've got FBD, I should be able to take the moment and figure out what that is. So I have this 400 Newton force, and it is acting at 0.5 meters plus 0.2 meters from A, so 400 times 0.7 meters. And notice that's actually going clockwise, so this is negative. So negative 400 times 0.7, that's our first half. And then we're going to do our FBD. Now we do have to split it up into X and Y components, but we can still figure out what FBD is from this. So my X component here of FBD, we'll notice that because these two lengths are equal on the member, that this is a 45-degree angle. It's a 45-degree triangle, right? A 1, 1 square root 2 triangle. So here, this is 45. So this distance we said was 0.2, and this distance was labeled as 0.1. So for my x component, it would be FBD times 0.2 times the adjacent here, cosine 45. And we'll notice this is positive, right? It's going counterclockwise, so this is a plus. And then finally we have our other component, our x component, or our y component, sorry, of FBD. FBD. So that would be FBD sine 45, the y component of FBD. And it's 0.1 away, and it's also going counterclockwise. So it's positive. So that's our moment setup, right? And this is an equilibrium, so we set it equal to 0. And now we can plug into our calculator and solve for FBD. So when I plug all of that in, I get FBD equals about 1320 newtons. 1,320 newtons. I rounded a little bit, but it's about 1320 newtons. So now that I have this FBD, I can set up my other two equilibrium equations and solve for AY and AX, since that's what it asked me for. The question never actually asked me for FBD, but I needed that in order to find AY and AX. So I'm going to go ahead and move. I'm going to get rid of this guy. Move you up here for reference. Okay. So I can do my X or Y. It doesn't matter. You can do whichever you prefer first. I'm going to go ahead and do my Y equations first. Some of our equations in the Y direction equal 0, which is going to be our AY minus this FBD Y component minus FBD sine 45. So I know FBD, it's 1320. I'm so sorry. Excuse me. So I know FBD, it's 1320. So if I solve this, right, this equals 0, I get AY equals 1320 times sine 45, which is going to give me 933 newtons in the positive Y direction. So that's one force, and now I'll need to find my other one, and I can do that with just the summation of the X forces, with to the right being positive equals 0, equals 400 from our applied force up here, right? We don't want to forget that. 400 plus, oh, not plus, minus, actually. These are both in the negative direction. Minus AX minus the X component of FBD cosine 45. Of course, I can plug all of that into my calculator, and that gives me AX equals 533 newtons to the right. Now, of course, it did ask me for the magnitude of the force on the pin at A, so I might combine these into one single force, right? Do square root of the squares to find what the actual magnitude of that force is, which I did not calculate. Let me plug that into a calculator real fast. So if I do square root of 933 squared plus 533 squared, I get that the magnitude of the total force on FA is about 1075 newtons. And this would be my final answer here. You could leave it as either one of these answers, but it asks for the magnitude of the forces on the pin at A, So I would probably do a combined magnitude on that one. So that's an example of how two force members work, how they simplify into one single force. And you're not going to see these a ton right now, but when we get into trusses and some other things down the line, these two force members are going to pop up more often.